Good day all. Today from this session we are going to discuss about the previous year question paper in the chapter 14, Semiconductor devices. In semiconductor devices of electronics, materials, we are going to see the subtopics of intrinsic semiconductor, extrinsic semiconductor, P-type, N-type semiconductors means what, and rectifiers, full wave rectifier, off wave rectifier, diodes, the types of diodes we can say that PN junction, light emitting diode, and solar cell. These are all one by one elaborately. Let us see that. Yes, students. Chapter 14, Semiconductor Electronics. Points to remember. Some of the points you must remember and you have to know the formula. First point, a pure semiconductor is called intrinsic semiconductor. The semiconductor are mixed with impurity. Mixed with impurity, this term we can call it as the process of doping, right? So when the semiconductor is doped, that we can call it as extrinsic semiconductor. That means mixed with impurity. Doping, we said, dope with the semiconductor which is doped with the pentavalent impurity. For example, the pentavalent we can say antimony or arsenic. That type of impurity when we added with the semiconductor, that we can call it as a N-type extrinsic semiconductor. The doping process with the trivalent impurities like indium or gallium, that type of semiconductor is a P-type extrinsic semiconductor. Understand, children? Yes. The impurity atom, if suppose it is an N-type, means that is a donor. And the impurity atom with the P-type, it is an acceptor. And the electron mobility is always higher than the holes. And the mobility of a charge carrier, we can define as, that is denoted by mu. The mobility of the charge carrier denoted by mu is defined as the velocity, which is the drift velocity, which is gained by the electric field per unit electric field. So that we can mathematically relate that mu which is equal to Vd by E. So what are the type of diodes which we are seeing? That is for PN junction diode and LED, light emitting diodes, photodiodes and solar cell. See the PN junction diode, we can say that the PN junction diode, which is nothing but the two different materials, that is P-type and the N-type, two electrode semiconductor devices which allows the electric current in only one direction, while the block of the electric current in opposite or the reverse direction. So the PN junction which it forms when the P-type and the N-type. So P-type and the N-type semiconductors are joined together, we can call it as a PN junction. The LED, light emitting diode, we can say that the light emitting diode, which is nothing but this is a specially designed diodes which it gives the light radiation when it is the forward biased. See the LED which are made up of special semiconductors such as gallium, arsenic, this and that. So that is the light emitting diodes. Photodiode. See the photodiode which is nothing but it is a PN diode, PN junction diode. It's a pair of the electron and the holes are created by the junction in the photoelectric effect. So this we can explain in a different question also. Solar cells. Solar cells which is nothing but it is based on the photovoltaic effect and one of that semiconductor region is made, it is so thin. So that only we can say the light incident on it reaches the PN junction and get observed, right? So these are all some types of, these are all the types of diode which is given in our book. This is only that for this academic year for you, you have to concentrate based on this diodes, right? And we have rectifiers also one by one. Let us see, children. So now we'll see about half wave rectifier and full wave rectifier. First, let us see half wave rectifier. See, this is the diagram for the half wave rectifier. This is the input which you are giving. So we'll get the output like this. So what is the half wave rectifier? The working of the half wave rectifier, actually it transforms AC voltage to the DC voltage. And a half wave rectifier circuit which uses only one diode we are using it, okay. And this rectifier, we can say the half wave rectifier, which we can say that this is a type of rectifier and allows only one half cycle of the AC, right. So that is the waveform to pass while blocking the half circle. Understand, children? So this is the output from the half wave rectifier. And this we have a diode, right, and a transformer, and you have a resistive load, okay, resistive load, one diode, you have one diode, and you have this transformer, and as well as you have one rectifier load. How it is working? See, a high AC voltage which is applied to the primary side of, this is the primary side of this step down transformer. To obtain the secondary low voltage is applied to the diode. Then this diode is forward biased during the positive half cycle of AC voltage and reverse biased during the negative half cycle. So finally you will get the output waveform as shown in this diagram. As we said, the half wave rectifier will pass only one half of the cycle by using only one diode. Understand the concept, children? Now we'll move on to that full wave rectifier. See the diagram. See the full wave rectifier constructed with the two ways, right? We are using the method of the center tap. By the center tap, and also we have it consists of two diodes and one RL output for that purpose, and this is the transformer. So this will give the D1, D2, that full, you will get the full rectified form of the output, right? So these are all the input which you are giving. So this is the output form. So this is the waveform from A and this is the waveform from B. So we'll get this is the output rectified circuit. See, this arrangement we can call it as a center tapped full wave rectifier, children. See that? So this we are using the standard transformer with the diodes and it is working. How it is working? See, the input AC supplied to the full wave rectifier is actually very high. See, the step down transformer is in the rectified circuit which converts the AC voltage into the low AC voltage. The anode center tap diodes is connected to the transformer secondary winding and it is connected to the load. Okay. By that way you will get the output. So during the positive half cycle, diode D1 is forward biased and it is connected to the top of the secondary winding. Now at that time D2 is reverse biased as it is connected to the bottom secondary winding. So due to this, D1 will conduct acting a short circuit and D2 will not act on it. So while D1 is connected and act at the time, you will receive for D1 only the output. While the second half cycle when it is working, that time the D2 output only you will get. So that at the end of that, you will get the full wave rectified, the both output, you will receive it through the full wave rectifier. Understand, children? So this is the output for the full wave rectifier. See the question, child. How biasing in diode used in rectification? See, actually biasing which is there used in the rectification, it is actually allows the current to pass only when it is forward bias. So while the rectification, it allows only the current to pass through the forward bias. So when an alternatively voltage is applied across the diode means the current flows only during the part of the cycle which is at the forward bias at the time of rectification. Right. And what happens to the width of depletion layer of a PN junction when it is forward biased? At the time of forward biased, the depletion layer will get decreased. At the time of reversed bias, the depletion layer of the PN junction will be increasing. Got it? Next one is, why is photodiode used in reverse biased? See, the current which is passed through the forward bias will give major carrier. Whereas, we can say the current which is through the reverse bias, it is a minor carriers. So that the fractional change which is there occurring in the reverse bias due to the minor carriers, the current due to the photo effect, the photoelectric effect is more, and it is very easier to measurable while at the reverse bias. So that only the photodiode we are using the reverse biased. You can mention the important consideration which is required by fabricating a PN junction diode to be used as a light emitting diode, and what should be the order of the band gap of the LED, that is light emitting diode, if it is required to emit light in the visible range. See, we can say that because of why we are using the fabrication of the PN junction diode, it is heavily doped PN junction. The light emitting diode is a heavily doped of the PN junction diode, and the reverse breakdown voltage of LED is very low. Because of these 2 points, we are using this as a LED PN junction diode. We can be used as a LED. And also we are saying that we asked in that question, what should be the order of the band gap of the LED if it is required to emit light in the visible range? See, the order of the band gap, we can say that it is about to 3 electron volt to 1.8 electron volt. It is about to 3 electron volt to 1.8 electron volt. This range we can use it for the band gap, right? Yes, students, some set of MCQs and fill-ups we can see. The first question, the resistance of semiconductor is, how it will be? The options they have given: A, higher than conductor but lower than insulators, and B, equal to the insulators, C is lower than the conductors, option D, higher than the insulators. See, the resistance of, the range of the resistance in the semiconductor is higher than the conductor but lower than the insulators, we can say. Option A is the right answer for the first question. The second question, energy gap. What is the energy gap range of the semiconductor? Option A, equal to 0 electron volt, then less than 3 electron volt, C is more than 3 electron volt, and D is more than 12 electron volt they have given. The energy gap is less than 3 electron volt. Okay, in semiconductors. And in intrinsic semiconductor, how it will be the electron and the hole. The number of electron they have given, first option is number of electron which is equal to number of hole, and number of electron is greater than number of hole, number of electron is less than number of holes, number of electron will be 0. So in the intrinsic semiconductor, number of electron which is equal to number of holes. Next question, rectifier is a device which converts, option A, high voltage to low voltage, option B, low voltage to high voltage, option C they have given AC voltage to DC voltage, that is alternative current voltage to the direct current voltage, and option D, DC voltage to AC voltage. So the rectifier device, whatever the full wave or a half wave rectifier, it helps to from AC voltage to DC voltage. It converts AC voltage to DC voltage. So option C. And the PN junction diode conducts only when it is in a forward bias. Okay. Next question. Number of diodes which is used in half wave rectifier. So only one diode used. Okay. In full wave rectifier, 2 diodes used, right? Yes, the question is, why is a photodiode operated in the reverse biased mode? And B, the subdivision question, for what purpose is a photodiode used? And draw its IV characteristics for the different intensities of the illumination. The first part of the question, they asked about why is a photodiode which is operated in the reverse bias. As we already said, the fractional change which is there in the reverse bias, which is more than the forward biased, right? So, because of that, fractional change which is there in the reverse bias is more than the forward bias. So that only we are using the photodiode, it is operated in the reverse biased mode, and current with the the intensity of the light is more prominently we can see in the reverse bias also. So what is the purpose is the photodiode which is used? The photodiode which is used for the purposes, we can say that the detectors, and we can say that is the demodulators and all we can say. See, the detectors and for that demodulators. Right. And for the next question is draw its IV characteristics for the different intensity of the illumination. Right. So this is for the reverse voltage and this one is for the current which is measured in mu ampere. So this is the different intensities. We can take it if suppose I1, which means so this you have taken I0, I1 and I2 current, which means we can say I2 which is greater than I1 and which is greater than I0. This will be the output of the different intensities which is we are getting for the reverse voltage with the current. So draw the energy band diagram for an intrinsic semiconductor T which is equal to 0 Kelvin and T which is greater than 0 Kelvin. This is for the diagram of T which is equal to 0 Kelvin. See the energy band for the conducting and this is the balancing band they have given. See, this is a temperature at 0 Kelvin. An intrinsic semiconductor will behave like an insulator here. Here it will behave like an insulator and there is a small gap between the valence and the conducting band is in the semiconductor. So this image will explain for the T, the temperature which is equal to 0 Kelvin versus this diagram which is for T is greater than 0 Kelvin, right? So this will give for the, these are, we can thermally excited of the electrons at T which is equal to more than 0 Kelvin, right? And it is partially occupy the conducting band. Therefore, the energy band diagram of an intrinsic semiconductor will be shown in that second diagram. There some electron are shown in the conducting band, right? So these have come from the balancing band which is leaving equal number of holes, right? By observing you may understand that. By equal amount of holes will leave here, it will be move on to that conducting band. So these are the diagrams of the energy band for the intrinsic semiconductor, temperature 0 Kelvin and this is more than a temperature which is more than or above 0 Kelvin. Yes students, so far we have learned from this session about various questions we have achieved from semiconductor devices of PN junction, how the PN junction used, photoelectric diode, photodiode, solar cell. These are all we have studied. Thank you, students.